Well, good morning. Don't have a whole lot to talk about this morning, but we have 64 paid members right now. Our current balance is $2,204.85. So doing pretty good on all that. Only one thing I do want to mention, I don't know how many of your communities are part of IPW-MAN. It's Public Works responders for your communities. You join if you need help during a disaster. They'll work up 5 days in your community for no charge. It's just mutual aid, and if you need help, you call it. They send a crew down if you need trucks, chainsaws, chippers, or whatever. And one thing they ask in return is if in your region you need to reach out to if somebody needs help in a disaster, you go help them. It's Illinois. I think most of us be about region 7 here. It's cheap insurance. I think ours for our community is under $200 a year. So if you have a disaster, there's no way we're going to be able to have chippers and enough trucks to handle any kind of major disaster. I mean, we rely on Peoria, East Peoria, but if they get hit, they're not coming to help us. But they give you 5 days free of charge from each community that comes down. So just something to think about. Get on their website, look at it. Like I said, it's cheap insurance. So I'm going to turn it over to let Hunter do the introductions from Gas Voda, and we'll go from there. Thank you.
Rich, can you guys hear me okay? A little bit good. My name is Hunter. I'm with Gas Voda and Associates. I've been with Gas Voda about 7 years now. A little bit about me, I grew up in Tinley Park, which is a suburb just southwest of Chicago. I currently live in Northwest Indiana. I have a daughter named Addison that turns 2 in a couple weeks. I have a 3-year-old black lab at home, and we have a 10-year-old Shih Tzu who runs the house. He's the ankle biter, and he will bite you. So anyway, I appreciate everyone coming in today. Appreciate everybody tuning in online as well. We've got Brent here from Grundfos today to talk about dosing first. And then we'll probably talk a little bit about wastewater in general, submersibles, and possibly some booster pumps. So without further ado, I'll turn it over to Mr. Brent. You guys have a mic here. I feel like I'm the president or something. That'd be a little scary.
All right. So good morning. My name is Brent Nybarger. I'm with Grundfos. So I live in Indianapolis. So I drove over here last night and stayed in the Embassy Suites right across the river there. So I'm a district sales manager with Grundfos. I cover the water utility market, so wastewater and clean water. I have the upper Midwest region, so that includes Illinois, and I've got Ohio, Michigan, and I go over to the Dakotas and back down to Nebraska and kind of back over. Gas Voda and Associates is our local distributor. So they are, I'm just going to put this over here real quick. So they carry us for the water utility market. So they have Grundfos for basically the whole north half of Illinois and the northern third of Indiana. Thank you. So anyhow, 37, graduated from Purdue with a degree in construction management, worked at, built wastewater and water treatment plants for construction companies in Colorado, Atlanta, and then back in the Indianapolis area. And then I just got an MBA from Butler. So been working for Grundfos for the past 7 years. Actually, part of that 7 years, I worked for Peerless Pump as an application engineer. So working on the split case pumps and turbine pumps, working on the kind of the clean water. So anyhow, been a part of the Grundfos family for 7 years. So today we're going to talk about metering pumps, chem feed pumps. What's the other? Metering. There's a number of names for dosing pumps for this type of technology. So I'm going to talk more about Grundfos, but this does kind of apply across to a number of different technologies and manufacturers across there. So anyhow, I'm going to get going here. And if you guys have any questions, please let me know so I can address those and make sure you guys get your answers, and so you don't fall asleep. Yeah. So in today's market, I'm trying to stay in the camera here. So in today's market, it's all about, trying to be digital and be autonomous and be able to do things remotely and not have to have the human aspect to it. So, we have that. We're going to put that spin on this for the presentation, and how our pumps are accurate and how they can help you save time and money. So with chemical pumps, dosing pumps, safety is always the utmost concern. So these pumps are designed to handle tough chemicals. So your sodium hypochlorite, so your caustics, parasitic acid, whatever you guys are using out there in the market. By the way, what are some of the chemicals that you guys use for dosing pumps? Do you guys? Sodium bisulfite? Yeah. Okay.
Well, with diaphragm pumps, sodium hypochlorite, they have problems with gassing.
Yeah. Right. Okay. We'll talk about some of that and how we can hopefully address that for you. Okay. So anyhow, so safety's obviously very concerning. Basically, when you're treating water, you're literally introducing a poison into the water. So you have to have pumps that are accurate, dose correctly, dose on time, all that good stuff. So you don't want to overdose, right? Because one, you're either going to be wasting money on chemical, and then two, you're just going to be, you could obviously have poison people, right? So, and then the opposite is true. You don't want to underdose because then you have disease and things like that can be generated in the water line. So that's something that's kind of stuck with me is you're literally introducing a poison into the water line. So it's something you got to be really cognizant of when you're talking about chem feed pumps. So today we'll talk about some of the benefits of the Grundfos dosing lineup. We'll talk about how we have a simple system, how we can eliminate pulsation dampeners, how we can eliminate, let me back up, how we can eliminate a VFD on your dosing pumps, how we can eliminate a inline mixer, a static inline mixer, and a pulsation dampener. Is everybody familiar with what an inline static mixer is? I can kind of talk about that a little bit later as we start talking about like pulsations and things like that. But basically, you have a water line that's connected to this, and that helps to kind of distribute and mix chemical as you're dosing into the water line. So I'll kind of talk about that. And then a pulsation dampener helps to dampen pulses from a chem feed pump. So as it's dosing out, sometimes you can get pulses, so a pulsation dampener helps to mitigate that. And with our pumps, we can eliminate those, which saves cost, right? So we'll talk about how we can make selection of your pumps simple and how we can make integration easy for you, and maintenance also too. So what are the basics of a chem feed pump? So you have to be able to control the pump. So there's a lot of different types of pumps. There's either you can vary the stroke length, you can vary the frequency of the stroke, so the rate. So you have some method of controlling a metering pump. You also have the liquid end or the wet end of the pump, okay? And then you have, on this particular diagram, this is a conventional motor here, so you can have a conventional motor. You have some sort of way of driving the pump, and then you have a way to convert that rotary motion into a reciprocating action. Any questions? And I'm going to spend a lot of time talking about diaphragm pumps. The other alternative that's out there in the market is a peristaltic pump. What kind of pumps are you guys using out there? Are they a hose pump or a peristaltic pump or a tube pump? Or are you guys using diaphragm style? Peristaltic? Yeah. Okay. What? Both? Just, what's the, is it cost? Is it just availability?
The wastewater feeds ferric chloride. We just have some LMI diaphragm pumps.
Yeah.
And then the water treatment uses some peristaltic.
Okay. Okay. So we'll talk about the control and the drive in today's presentation. So on a diaphragm pump, this is kind of a schematic of a diaphragm pump. You've got the liquid end over here, okay? So the liquid end has a diaphragm. Our diaphragm is going to be a Teflon, a PTFE diaphragm. And then you have a suction check valve, and you have a discharge ball check valve. Oops, back up. So on the suction stroke, the diaphragm is pulled back. The liquid or the chemical is drawn in. So the suction valve is pulled up, so the liquid is drawn in. That discharge valve, ball check, is kept closed. And then as on the discharge stroke, the diaphragm is pushed forward. That causes the suction check to close and open up the discharge check. That's kind of just a basic on how it works. So let's talk about control based on pump stroke length control. So every dosing pump at 100% speed is going to have this sort of profile. So the red would indicate chemical that's being dosed into a line, okay? So you've got your dosing pump over here. It's pushing chemical into the line. So it's going to say, okay, 100% chemical. It's got a full stroke length. It's moving back and forth. It's pushing chemical. And then it's drawing back. And then you've got a gap in there. And then it's pushing chemical out. And then you've got clean water. So it's kind of like that's 100% speed, right? So if we have a pump that is controlling the amount of chemical based on pump stroke length, we're only going to have, say, if we want to, dial it down to 50% of the dosing rate or of the chemical being dosed, you're only going to have a 50% stroke length going through here, and then kind of further on, we've got 25% stroke length, and I'm building up to what I want to tell you guys. So this is what a kind of a flow pattern for a pump based on stroke length is. Pump frequency control. So this is on off, and then there's a pause on off, pause on off. This might be like a solenoid driven style diaphragm pump. So a diaphragm pump with a solenoid motor on it. So again, every dosing pump at 100% speed, no issues. It's the same profile. This is the profile of it being reduced down to 25% speed, so it's on off, and then there's a pause. And then again, 10% speed, it's on off, and then there's a longer pause, and then it comes on again. So you can see there's gaps in the chemical being injected into the line. Now a pump with a variable frequency drive. So this is going to be, again, 100%, and then a 50%. So now your pump speed has slowed down. So you have your discharge stroke, which is the red. That's the chemical being dumped into there. You're having a 50%, and then you have a 50% suction stroke. So that diaphragm is pulling back that same amount of speed. So if it was 1,800 RPM at full speed, now it's going back, at 50%, it's 90%, or whatever, 1,800, 900 RPM back. So it's, you know, it's a lot slower on the suction stroke. So that's how pumps work if they're done on a variable speed drive. Dosing pumps anyhow. So I'm going to talk to you about stepper motors and how we use stepper motors in our dosing pumps to make a difference. Come on, I know those EPA guys. You guys got something. All right. You have a rotor, and then you have a number of these coils that are energized independently around the rotor. So I'm going to kind of talk about this as I'm going to go super high level. So you have a rotor, and you've got a bunch of teeth on a stepper motor. This is the rotor here, okay, and a bunch of teeth. And then outside those teeth, you have more teeth that are connected, that are energized by coils. So there's kind of a number of different zones here that can be energized based on a microcontroller in our motor, or in our pump. So you can vary the voltage, and it allows basically super precise movement. So right now we have 50 teeth on this rotor. So we have 50 teeth, and I'm going to go high level again, but there were 4 steps per tooth. So we have 200 steps. So basically that rotor can turn kind of 200 different increments as it's making a full rotation. But now, so that's, we'll consider that's 1.8 degrees. So now, but we have with a microcontroller, we can change that full step down to a half step, down to a quarter step, to 16th to 3200. So literally, that's why it's called a stepper motor, because it can micro step. So stepper motors are used on robots and factories where you have high torque, high precision. They're used on 3D printing. I didn't bring a 3D printed model in here, but things that have super precision and high torque is when stepper motors are used. So you have the greatest control when you can slow down that pump and you can introduce more steps into the action. So let's see if we can get this thing to roll here. Oh, let me go back here. Yeah.
That's Kurt over there. By the way, Kurt, can you introduce yourself? I think everybody here knows me. Who are you? I'm sorry for those of you that know Kurt. I don't know how he found his way here today.
All right, so this is just an animation showing, if I can make it work. There we go. So that's just the stepper motor. You have the coils around here that are energized at varying voltages to make that kind of turn. And then here is our diaphragm and how that stepper motor pushes that diaphragm back and forth. And how that works. So anyhow, do you guys have any questions with that?
Stepper motor, though, sucks back real quick. Dial it down, but then it takes its time and it pushes it all the way out. Unlike a solenoid pump that's always pumping, pushes it out nice and slow, and it sucks back. So what you're actually doing is you're putting more chemical into the water over a longer period of time, so you don't have the gaps that he was showing you in the other ones.
Here we go. All right, so from current slide.
You guys can't see that are watching online, obviously, but there is a demo unit over there that you guys can play around with in between the break, see how it works, and just kind of put your hand on it a little bit.
So let's talk about stepper motor and speed control with a stepper motor. Again, kind of 100% speed. It's all the same. It's all the same across all different designs of pumps. So like Kurt was saying, on a stepper motor, we have the ability, what it does, so if we lower that speed down to 50% speed, that discharge stroke is going to slowly discharge 50%, but then it has a very quick suction stroke. So that suction stroke pulls back very quick, And what that does, that allows you to have very minimal gaps in your dosing, so that when we talk about eliminating the need for a static inline mixer, that's what that is able to do. And you can see when we talked about we have the greatest control at even slower speeds, you can see we can dose very, 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 very slowly, and then we have a short gap, and then we can dose again. So when you're dosing very small amounts of chemical is when we have even the greatest impact. So high turndown ratios, let's talk about the benefit of what Kurt was talking about, a high turndown ratio. So in traditional or conventional pumping, you might have a number of different products. You might have up to 10 products. You might be able to need to hit different flows and different heads and times of day and speeds and whatnot. So with a high turndown ratio, on this model, the DDA, you can do 3,000 to 1. So what does that mean? That means if that pump is actually a 2 gallon per hour pump, I can turn it down to 0.0075 gallons per hour. So it's basically like a teaspoon per hour that it can dose. So it's got a high turndown ratio. So the more you turn it down, the greater accuracy, or the greater, let me back up, the greater benefit you get, okay? So this particular demo unit is a 2 gallon per hour unit. We do have, obviously, much higher flow pumps as well, and it does up to 232 PSI. Kurt, anything you want to add on this? I'm going to keep going, but I feel like you've got some good comments you've made. So we do have online an ability to make pump selection yourself. You can go on, if you Google Grundfos dosing pump selector, you can do that. It's basically 4 steps. You put in your flow control, or you're putting your capacity, so your quantity of chemical you want to dose, your discharge pressure, how you want to control it, analog if you want digital controls on it, remote start and stop, graphical display, and then the type of chemical. So in this instance, we have a number of preloaded chemicals on there as well. So sodium hypochlorite is pretty common. So we've got that shown there. So let's talk about drive strategy benefits to the stepper motor design. So we've got 100% suction and discharge stroke. So what that does, we always know we're not varying the stroke length. We're always got that cylinder, that wet end that's always going back, the diaphragm is always pushing back and forth, so we are always able to calculate the exact amount of chemical that's being dosed. We have on this air bubble detection. So we talked about parasitic and sodium hypochlorites that were, that off gas. This has air bubble detection, and I'll kind of demonstrate that in a little bit. We have a feature that's called auto-deaeration. So a lot of times municipalities are not producing water maybe in the night. So these pumps are sitting on top of sodium hypochlorite. It off gases. These pumps auto-deaerate every 20 minutes. So it gets that air bubbles out through the wet end. So when the pump is called to turn on, there's no air in the line. There's no air in the wet end. So let's talk about adding a sensor control. So we have a sensor on these pumps that's basically a pressure sensor. So it's basically an indication of the dosing head volume. And we can determine when there's air in the line, when the pressure has changed in the line that we're dosing into, so we can speed up the pump, slow down the pump, always to get that accuracy and that set point that you always want to dose chemical to. So we can prevent overdosing and underdosing. So how does the pump detect problems in the system? So normally in a system you would have a pressure indicator, some sort of flow meter into the pump. So let's talk about how we can maybe eliminate that. So if you kind of caught that, so this is a dosing pump up here. Here would be your pressure gauge. Here would be your flow meter. Excuse me, here would be your injection quill or your injection point into the line. Here's your foot valve that's pulling out of the tank. So let's talk about how we can maybe eliminate a couple devices that you normally would have. So flow control and measurement here. So this is what's called a performance chart. Normally on a centrifugal pump, you have what's called a pump curve. On a chemical feed pump, you have what's called a performance chart. So this is just kind of showing the different phases of how that chemical is brought into the wet end and is compressed and metered and pushed out. So it's almost, if you think about, like, back to shop class, like you think about a 4-stroke engine or whatever. This is kind of what we're talking about here. So so we've got pressure on the y-axis, and we've got stroke position or stroke stroke position on the x-axis. So your first part is your compression phase. So as that liquid is drawn in, that diaphragm is slowly starting to push. So it's compressing that liquid. And then, and then you have the metering phase. So that diaphragm pushes that liquid out, and we're metering the liquid as it goes out, and then that diaphragm pulls back. We have an expansion phase. So again, now this diaphragm is now moving back, and then we have the filling phase. So this is almost like, think of that diaphragm being here, and it's pushing, 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 and then now we're up at step 3, and then it starts to draw back, so it expands, that chemical expands, and then you've got the filling phase, bringing that chemical back into the wet end. That's kind of just a little bit of tidbits there. So flow control, think of it like we're able to diagnose air bubbles, we're able to diagnose leak detection with a pressure sensor that is on these pumps.
We'll give a demo here of when it goes into that mode. I guess you can
Right.
see what actually happens. It's hard to tell on the presentation when you see it in person. You can tell exactly what's happening.
Yep. So when we have air bubbles, so normal operation of a pump would be, if we looked kind of more, it would be, more like this, almost this blue line. That'd be normal operation of the pump. If we had air bubbles in the line, that compression stroke, it's going to keep, because air does compress. If there's air in the wet end, it's going to notice. We have a kind of a microcontroller on the pump, and the controls on it will notice via that pressure sensor that there's air in the line. So it will notice that, and it charts that. And then at that point, it knows that it needs to speed up to try to push those air bubbles out. So it's got kind of that auto detection feature. Kind of the same thing with cavitation. So if you have a plugged suction line, so if you have the number 3 here, you might have a plugged suction line. It can detect that and deliver an alarm and a warning to you as well. So and all that can be sent remotely, so you can know that you need to come out and check things and whatnot. So that.
Either way, if it's on the suction where it notices it doesn't have any liquid, it'll speed up. If it notices that it's not getting that point again, it will send out an alarm. So it sends out an alarm either or, on high pressure or if the pump is not pumping properly.
Yeah. So again, we're kind of talking just more flow control. I'm going to buzz through some of this, but this is just, again, talking more about performance charts and how this pump actually has brains in it and can determine what it's, kind of what is happening in the system. So it basically adjusts its speed based on what we're seeing is happening. The pumps do have kind of a red light, green light, yellow light. So red is basically an alarm. Yellow would be like a warning. And then green would be kind of like everything's good. Everything's working. So flow measurement, just a few formulas for you. So the general formula for calculating flow rate is the change in volume over the change in time, so delta V over delta T. And then applied to a dosing pump. So stroke volume is divided by stroke time. So your amount of volume in your stroke length divided by time. That's basically how you determine flow. So let's talk about the effectiveness of your stroke length and maybe how our pumps might be able to help you there. So this is an ideal stroke without a fault. We kind of talked about that. We've got that compression, then the metering, then the expansion phases, and then the filling phase. So this is kind of an ideal performance chart. And so we're just going to talk about the effective stroke length. Say, for instance, this would deliver 5.9 liters per hour. We're talking metric here. I know we're here in the US, but this is just in liters here. So if we had a cavitation going on, the indicator would then determine that, oh, I'm only pumping 3.78 liters per hour. Something's wrong. I need to do something to compensate for that. So with our auto adapt, it's kind of like cruise control for your pump. So again, we've got that pressure sensor that I'll talk about. So we've got what we have our target flow, say 3 liters per hour, and our measured flow, 2.99 liters per hour. So we're always trying to hit the target, and we always display what our measured flow is. So here we're pretty close, but what the pump is going to do is try to get up to that 3 liters per hour. So it's going to speed up. So flow control and measurement. Let's kind of talk about a few of the things here. So we can eliminate, let me back up. So we eliminate the pressure sensor because we have that built in to our pump. We eliminate the flow, flow measurement because we have that built into our pump. So basically the Grundfos DDA is kind of a flow indicator, transmitter, flow control, pressure indicator, pressure transmitter, all in one. So we've kind of thrown a schematic here that we all have that included. So it kind of helps you save a little bit of money there. So again, it's all about automation with a dosing pump. So I'm going to, do we need to? Okay. I can be pretty quick here. So I'll kind of show you a few of the benefits of this dosing pump. Let me see if I can bring this over here real quick. Yep. Yeah, I think that might be good. Maybe to. Oh, I thought it might be good to bring it over to that table for a second. So let me kind of get this going for a second. I have had it off for a little bit, so I know there is some air in the line.
Can you see that with the camera doing it this way?
I need to get some
As long as Brett gets
water
out of the
going
way.
through it. So as I just started up, it has have air in the line, and you're seeing that it's noticing there's air because it's sat in my office for the last couple weeks, and it's been on an airplane, blah, blah, blah. So it's speeding up. It's trying to match that set point, and it's trying to push that air through. And then you'll see it slow down as it does match the set point on this set point. So we have 5.54 gallons per hour. Can you guys see this or no? Yep. Yep. Let me make sure I cover everything. I just want to make sure we're good there.
We put some of these in Morrison, and Morrison has fluoride that's a 0.4. We turn this down to a 0.200, and then dial it in with the acknowledgement on there, and they stay right at a 0.7 for their fluoride because of the turn down for it. It worked pretty nice.
So a few benefits of this. This is your dosing head, your wet end here. This is acrylic. Normally, this is because this is a display model. It's not acrylic. It's either polypropylene, PVDF, or PVC, so it's some sort of black material. But we just have it acrylic so that you can see that diaphragm pulse moving back and forth. The wire on this is your pressure sensor. So here's your pressure sensor that helps to tell the pump kind of like, hey, I got issues, I got things going on. And it's all about what it's injecting into the line, what that pressure is into the line. So it can determine back pressure, and if there's air bubbles, if there's leaks going on. So let me kind of demonstrate, like, say we're pumping into a line that's 60 psi, and then all of a sudden it jumps up to 80 psi. Well, if you have a dosing pump that you've kind of set and forget about it, and the pressure changes, you're going to be underdosing, because that pump is not going to know, like, oh, I need to speed up because the pressure in the line is now 20 psi more. So you're going to be underdosing, okay? So I'm going to demonstrate that here. You might be able to hear it speed up. Maybe. There was a slight change in pitch and sound. I do have it kind of, oops. Let me change it. Maybe if I change the speed. But if I lower that pressure, you can kind of hear it a little bit. It goes, it kind of slows down. It's hard to hear with a bunch of people here. But anyhow, it does, and I've basically simulated by this pressure valve here, I've simulated that your pressure is changing. So say that line was 60 and now it's 40. You don't want to overdose and waste money on a bunch of chemical, so it will slow down to match that set point. So it does have, this is your target flow. That's kind of that 0.054, I think is what it is, the one that's highlighted in black. And then you have your actual flow there as well. Yeah. So the auto deaeration, I should have had that. I can't really show that because the pump has to be off and it has to set for 20 minutes. During our next presentation, I'll set it up so that it's setting. But basically, this pump will be sitting on top of, say, a chemical tote or wherever you have it, wall mounted, floor mounted. And if it's turned off, it auto deaerates every 20 minutes. So like if you have an off-gassing chemical like peracetic acid or sodium hypochlorite, it helps to push those air bubbles from the bottom of the wet end up to the top. And so that when the pump is called to turn on, it's got a full dosing head full of chemical. But yeah, so I think maybe what you're talking about is if we do get air bubbles in the line, which happens, right, with chemical. So I'll kind of simulate that. You're going to hear the pump speed up a little bit to try to match that target flow, because the pressure sensor is going to say, I got air. I need to do something to try to push this air through the line and get everything back so it's perfect, right? Hunky-dory. So I'm going to make some air in the line here. Right. Yep. So it's speeding up. It's trying to push that air through the line. And this is about 1/4 the speed of this pump. It's about a 0.5 gallons per hour right now. It can go up to 2 gallons per hour. And you can change that all manually too as well. And you'll see the air bubbles through the line. And you'll see this is a flexible tube, so it's not pulsing. So that's why we say, we can theoretically get rid of the pulsation dampener. So this is all loosey-goosey, right? So it's not like, sometimes you might see like the line kind of flexing a little bit. So now the pump's slowed back down, now that it's got those air bubbles through the line. And that generated kind of an alarm menu. It didn't necessarily generate a warning. So a warning is like a safety thing, like it's going to shut the pump down. Or if you just have air in the line, that's not really like a safety thing. It's just like a nuisance, right? Like you want to get it fixed, and you want to have somebody to be able to come out and check out the pump, see what's going on. So like more of a, let me see. So if you have a block suction line, so if you have cavitation in the pump, so I'll kind of demonstrate that real quick. And that's almost like if you have air bubbles. But basically you have a block suction line. it's going to generate an alarm, but it's not going to be a warning. It's not going to stop the pump. It's still going to say like, hey, I got an issue, but I'm still going to try to keep going here. So it's right.
Is there a point when it just shuts itself off after a time limit? That it doesn't get to correct itself?
No, it's kind of like because it's kind of like a fire pump. Like, fire pumps are built to run to destruction. So it's kind of like that, unless it's like a safety thing. So I'll show you kind of once we get this alarm cleared. So now it's starting to slow down. Yeah, so yep. So we have what we call an e-box that I don't have on this, but it's basically, so we have a number of different IOs and control cables that can be connected to this, and then we have an e-box that mounts to the bottom of this that can communicate to Profibus, Modbus, whatever communication protocol you have. This particular model, let me see if I can get that off. Oops, I gotta go this way. So this comes with, the e-box would basically go between this and the pump. So it's maybe 1.5 inches thick, but it's got other ports that, you can control it remotely as well and get alarms and all that. So this pump comes with, you can either floor mount it or wall mount it. This is kind of simulating a wall mount. If you look on the back of this, it's got the mounting plate back there. So pretty easy, easy to install, that sort of thing. See if I can get it on there. There we go.
Another thing about this is nice is that red head on it. There's 2 little bolts. You can move that to 3 different positions. So you can put that any way you want on the wall. So that way, a lot of times you put them on there and you're looking at it from the side trying to, turn your numbers and that. Well, that top head can come off and it can turn to different sides. So you can put that pump either going this way or you can turn it straight out. You can put it coming back this way. It's
right.
It's made so that, it's easier for your operators to use.
So if you had a line burst on this, so say you've got your dosing pump, you've got a line run up to to wherever, to 20 feet away, right? So you've got some tubing or some PVC piping, say you get a burst in it, that's going to be a safety thing. So the pump will shut down and it will know when it has that type of an issue. So basically what I'll do by demonstrating that, I'll just lower the pressure down to something that's like nearly no pressure, right? Because it's going to be pumping in. Normally it's going to say, I'm trying to go to 60 PSI, but then it's going to say, I've got 5 PSI or whatever. It's going to know, so it'll shut down. So I'll kind of show that. It does take a second here. And it will, because I've messed with it a bunch, it will burp some air every once in a while. So there, it's shut down. So that's kind of like a safety thing where it forces you, it's like, I'm spilling chemical, you got to come out here and look, I'm not going to try to fix myself, right? So I'll just acknowledge that, and you got to come out and acknowledge the alarm, and then it's back working again. So we talked about if we had blocked line, we talked about if we had air bubbles, we talked about if we have a blocked or a broken discharge line. There's one other thing I want to talk to you guys about. Overpressurization, that's right. So does have a limit because it is a diaphragm pump. This particular model will go up to 232 PSI, but because it is a diaphragm pump, it has to have something in it to tell it like, hey, turn me off, because it will try to keep going over 232 PSI, it will, if it didn't have some sort of control in that. So it does have that alarm as well. So I'll try to get this pressure up over 232 PSI-ish. And you can change that too, like if you want it to be only 100 PSI and you want the pump to kick off if there's a 100 PSI or more in the line, you can change that in the settings. And get it up there. So there, the pump will kick off, and it'll say, oh, I'm over 232, or I'm over whatever you decide, so 100 PSI. So yeah, so do you guys have questions about a diaphragm, about what I've talked about here?
We'll let you guys touch it as well during the break if you guys want to mess with it. It's pretty proof. I might say if I'm able to do it, you guys can definitely do it. Let's put it that way. Curse God says this.
Yeah.
What's the life expectancy like on the hoses?
So this is every 8,000 hours, so every 2 years, it's you need to change out the diaphragm and those ball checks that I was talking about. So those are located, it's kind of hard to see, but those are located here and here. So you get a kit, a diaphragm kit. So you have basically an Allen wrench or a hex head key that you take off these 4 bolts, pull this off, and then by hand you just unspin the diaphragm, this Teflon diaphragm, unspin it, put the new one on, and then everything's all hand tight on these. Like when you're connecting these up out in the field, like don't use pliers, anything like that. It's just hand tight. Because you can use pliers and you get a little piece of plastic in there, whatever. It's just all hand tight stuff. So it's like a 20-minute change out, maybe. I mean, if you got good at it, you'd probably go faster than that. But it's every 8,000 hours, I guess. So the sensor is for the life of the pump. Yep.
Also on there, when it comes time for that diaphragm to be changed, it will actually go to yellow on there, and it'll tell you time to order a diaphragm.
Yep.
And it will give you the pump, the diaphragm
Part number.
that you need to actually order for.
Yeah. Yeah, it does have like a.
Actually, it's also in the menu. You can go to that and it'll say diaphragm, and it'll give you the number for replacing the diaphragm. So that's all in there also.
Yeah, and this does have an alarm history log up to 20 alarms. So the biggest thing is like when you first get it, just set up the date and the time so that if you are getting alarms at 8:02 p.m. every evening, like you can go back and see what's going on there. So, yeah, it's all
It's in English too.
English. Yeah.
Does this model have the capability of hooking up to like SCADA?
Yep.
Yeah.
Yep.
It's 4 to 20. It actually has hookups for relays to go out also, that you can turn on different stuff.
Yep.
Yeah.
Any other questions?
Where is your chemical feed expert in the area? If you guys have questions, definitely give one of Kurt's cards. Quite a bit more about this than I do. You guys can tell. So that's your guy.
I have one of those in my van at all times. I have a demo unit. So if anybody wants to see it, personally and mess with it, I can stop by anytime for you.
You usually put beer through it too, so if it smells, it's just,
Yeah.
hey, no mind.
So for changing capacity, basically you change the Teflon disc.
For changing, well, this particular model goes up to 2 gallons per hour. And then for changing capacity, I mean, this is our smallest DDA. So it's our smallest smart digital pump. But yeah, we have different flow capacities. This goes down to 3,000 to 1 Turndown. The bigger units go up to 1,000 to 1. So 1,000 to 1 is still pretty good. If you think about a traditional, like just horizontal NEMA motor that's 10 to 1 or 20 to, maybe 20 to 1, maybe. But it goes down pretty low. So.
So for budgeting purposes, what's the cost?
You want to, it kind of depends on the model.
Kind of depends on the model, depends on, cables you want with it, if the relay outlets and stuff like that, but.
3-4 grand,
Three.
3 or 4 grand, yeah, depending on, what you want. You can get different wet ends and a little more robustness. PVDF covers a lot of different chemicals. So there's a different price points, but it's all about. We do have a higher price point than maybe some others, but we do like to promote that we're plus or minus 1% on accuracy. So like, you spend a little bit more, but in the long run, you're saving on chemical, and the auto adapt and being able to you're always hitting your set point without having to go back and check your water quality. Of course you do that, but then maybe you might have to manually go back and adjust it. And so that's kind of the benefit of pay a little bit more, but you get, you kind of get a little bit more. So, yeah. So in gallons per minute or gallons per day? Oh, off the top of my head, I'd have to look. But we go, so traditional dosing pumps, like you're talking like gallons per hour, but we do go up to gallons per minute. So we have some pretty big pumps that will cover you. And most. Do you have pumps that do 3,000 a day?
Oh, yeah.
Yeah. What would that be per hour?
I know there's one of them that's like 232 gallons an hour.
Yeah. Right. That'd be for your bigger municipalities, so. Like this one, yeah. This one, exactly, yeah. So.
You guys are good. We'll do a quick break. If you guys want to put your hands on that, feel free. And just let the streamers know that we'll be back here in 10 minutes.
Okay. Yeah, we'll be back in 10 minutes. So it's 10:05 Central. We'll be back at 10:15 Central.
Tip your waiters. Don't freeze.
Yeah. There you